Speed limits are used to set the legal maximum or minimum speed at which vehicles may travel on a given stretch of road. Speed limits are a common element and an important element of review and analysis for traffic engineers. So I'm going to talk about why speeds are important, talk about speeds as a design control, safety impacts, neighborhood and local street speeds, the source of complaints, and what we can do to improve speed management. When we look at speeds, there are competing objectives when we look at mobility and we look at safety. On the arterial roadway side of things, where mobility is the focus, we're really looking for higher speeds, higher mobility. The complaints you may get is when there are no speeds or the speed of zero, meaning there's no mobility, and we see that when there's congestion on interstates and higher order arterials. Then on the other end of the spectrum, on a local street, a neighborhood street side of things, safety tends to be the overriding driver, and really the complaints come from when speeds are too high, and there's a sense of decreased safety, and that really applies on that neighborhood street design. And a lot of complaints come in to local traffic engineers as people complain about drivers through the neighborhood traveling at speeds that are higher than what they think are acceptable and safe speeds. And then I'll also talk about setting speed limits and using flexibility and documenting engineering judgment to set reasonable speed limits. So I'll start with design speed and safety impacts. When we look at the wide range of design speeds that are possible, that are based on the type of roadway, the terrain, and whether it's an urban or rural setting. And they can range from, a design speed can range from as low as 20 miles per hour on a local street up to 70 miles per hour or higher on a freeway. When we think about design speeds, this really isn't a specific design element, but it influences a wide range of other design values. Many other elements are affected by the actual design speed, but it's not something that in and of itself you're going to see or observe on a roadway. And when we think about the design speed, it's really the maximum safe speed under favorable conditions. Typically the speed limit is set lower than the design speed. General guidance is that if you don't know the speed limit or the design speed, that there's a 5 mile per hour difference. So if you go to a roadway and you see that the posted speed limit is a certain speed, we're going to add 5 miles per hour to that to assume the design speed. Obviously it's better if you actually know what the design speed is, but that's not going to be possible in every case. And design speed most importantly or most directly affects horizontal and vertical curvature. So if you look at the design of horizontal curves and vertical curves, they are highly impacted by the design speed that is selected. So the actual characteristics of those curves are highly influenced by the design speed. And design speeds can change throughout a roadway, throughout different segments of a project, but the focus, particularly in recent years, has been to gain some consistency along roadways, in that the more consistent we can have a design speed throughout a roadway, generally the more predictable and therefore the more safe it will be for a driver. So keeping design speeds within some level of consistency is useful and important. And generally drivers will know the design speed. They may not think of it as the design speed, but they will experience what that maximum speed is, particularly through horizontal curves, as they kind of push that boundary of feeling the acceleration and gravitational forces in the vehicle, and have some sense for what the design speed is for a given roadway. And curves are the primary way that drivers will experience the design speed. The designated design speed can and does differ from the inferred design speed and operating speed. So from the designated design speed is based on a lot of elements and values that go into the actual design of the roadway. So lane widths, curve radii, vertical rate of curvature, and other things. When we think about the inferred design speed, this is from the driver perspective. So as a driver drives along, what design speed is getting communicated to them? How do they understand the roadway? And that's highly related to the operating speeds, so the speeds that are actually used on the roadway that vehicles are actually driving them. And then if we look at risk, the larger deviation we have between successive elements in the design speed, the higher the safety risk is. So kind of going back to design consistency, if we have successive elements, so maybe we have two curves that are closely spaced, if the design speed differs by more than 15 miles per hour, that's a high safety risk. And so you'll tend to see a lot of signs and chevrons and things trying to communicate that information to us if there is a large difference in those design speeds between those successive elements. When we look at speeds, there's an important relationship between speeds and crash rate. And this diagram shows us the relationship between changes in average speed and change in the crash rate. So if we have a given road and there's some way that we can influence the average speed, it may be by different enforcement strategies, different engineering countermeasures, whatever it may be. So on that y-axis, if we can change the average speed, it has some relationship with the percent change in the crash rate. And the general finding from this study is that a 1 mile per hour change in average speed results in a 5% change in the crash rate. So if we can reduce the average speed by 1 mile per hour, we're going to reduce the crash rate by 5%. On the flip side, if the average speeds increase, so for some reason drivers feel that they need to increase the speed overall, the average speed on that roadway, every 1 mile per hour results in a 5% increase in crashes. So it's an important thing to think about on taking a given road, and if you can control or manage those speeds and keep those low or even decrease the speeds, if you have a crash problem, you're going to improve that safety performance. This is also spelled out in the Highway Safety Manual First Edition. This is the crash modification factors. These are multiplicative factors for crash estimates. And this is showing us the change in speeds on the vertical axis. So the far left column is showing us the change in speed from a new condition, from an initial condition to a new condition, and then the columns for each of the miles per hour are the initial speeds. So for instance, in this graph, the way we can read this, at 60 miles per hour, if the operating speed goes up by 5 miles per hour, so we're going to take that 5 miles per hour, we're going to come up with a CMF of 1.26. So that means that's a number we multiply our expected crashes by, or our original crashes by, and that tells us that we're going to see an increase of 26%. So 1.26, we're going to increase the crashes by 26% if we have an existing road and we increase those speeds by 5 miles per hour. On the other end of that spectrum, if we reduce the speeds by 5 miles per hour, we're going to end up with a crash modification factor of 0.75. So we'll multiply our expected crashes, our initial crashes, by 0.75. And that's going to lead to a decrease in 25%. So 1 minus the 0.75 gives us a 25% reduction in crashes. So this lines up with the previous research showing that taking an existing road, if you increase the speeds, you're going to expect more crashes. If you decrease the average speeds on that road, you're going to see a decrease in crashes. The Solomon curve is a famous relationship between average speeds and individual vehicles. So the previous data looked at just the average speed overall. So look at that whole vehicle fleet, the whole stream of vehicles on a roadway. What's the average there? This graph shows us what happens when individual vehicles deviate from the average speed of the traffic. So this is the average speed. So if a vehicle is traveling at average speed, this is going to be the prediction for crash involvement. And it's at a low point for these curves. We see a line for the dashed line is for nighttime, the solid line is for the daytime. And what this essentially shows that the greater the variation in speed of any vehicle from that average speed, the greater the chance of being involved in a crash. And we see it increase in that rate as it moves away from that average speed. So at small deviations from the average speed, so within 10 miles per hour, it's not substantially different crash involvement rates. But as we move well beyond that, so looking at 40 miles per hour below the speed, the crash involvement rate is huge. Similarly, at 20, 30 miles per hour above the average speed, the crash rates increase as well. And so this helps explain those individual drivers that are driving much faster or much slower than the average speed and that increased crash risk. We can also look at the daytime and nighttime lines and also see that just generally overall nighttime conditions are more hazardous. We're going to expect more crashes during the nighttime than during the daytime, and those trends follow, but there is that higher rate in the nighttime. We see similar relationships for increased severity at higher speeds for both injury and property damage. So on the left here we have the persons injured as a function of speed. So once you start hitting these larger speeds, the curve starts this exponential jump. So the number of people injured in crashes increases substantially at these higher speeds. Property damage similarly starts to go exponential at higher speeds as well. So speed is extremely important for injuries and property damage, both in terms of the number of individuals and the dollars associated with property damage. Similarly, we can look at fatal injuries, and has a very similar relationship with speed. At the higher speeds, the probability of dying in a crash climbs exponentially. Now, moving from people inside the vehicle to people outside the vehicle, specifically looking at pedestrians and their risk of fatalities and serious injury, speed is extremely important. At 20 miles per hour, 18% is our expected percentage of pedestrians that are killed or at serious injury. At 30 miles per hour, that goes to 50%, and at 40 miles per hour, that's at 77%. Part of this is related to the physics involved when there is a collision, that the pedestrian is much more likely to have forces that their body cannot sustain and lead to serious or fatal injuries. But also from a driver perspective, the cone of vision changes as the speed changes. So there's a reduction in that field and peripheral vision as speeds increase, and we can see that at 20 miles per hour versus 40 miles per hour. The 40 mile per hour cone is much smaller, and a driver is much more focused just on the roadway itself and not what's happening at the periphery. And that can be particularly important on local and neighborhood streets. Similarly, when we think about traumatic brain injury, the data quality is important when we think about how pedestrian crash victims are injured. And what we can see, what the data show, is that at all injury levels, as reported from local law enforcement, there are traumatic brain injuries that result. So even some crashes that were identified as no injury, the pedestrian ended up later having a traumatic brain injury as a result of that crash. And it was just that on the scene of the crash, there were no apparent injuries or only minor injuries in some of these cases, but when seen by qualified medical professionals, some of those crashes did result in traumatic brain injuries. So just something to think about. If we look at crash data, it's important, especially with pedestrians, it's important to know that any of these crashes can be serious, even if they don't appear to be, even if they appear to be even at low speeds, that traumatic brain injuries can result from injuries sustained from those crashes. So it's an important focus area to try to reduce pedestrian-related crashes. There was an Insurance Institute for Highway Safety study that was conducted looking at changes in speed limits, and this is a map showing us the maximum speed limits in January 1993. we can see that most of the country had 65-mile-per-hour maximum speed limits, and a handful of the northeastern states had a maximum of 55 miles per hour. And a lot of this wasn't done for safety, it was done for energy reasons. In the 70s and 80s, particularly in 1973, Congress required that states adopt the 55-mile-per-hour speed limit as their maximum speed limit to receive their share of highway funds. These concerns were about fuel availability, not safety. The measure was known as the National Maximum Speed Limit, but it had a huge impact on fatalities, reducing fatalities. 1987, the energy concerns were fading, and so Congress relaxed the restriction, allowing the states to increase speed limits to 65 miles per hour on rural interstates. And so that's why we see by 1993, most of the country had those 65 mile per hour maximum, and then the law was completely repealed by 1995. And so we're going to see the changing landscape. This was 1993. And this is 2013. So obviously a huge change in those maximum speed limits from 1993 to 2013. This doesn't mean each of these states set these as the speed limits on all their roadways. It just meant these are the states. The states had authorized at least some roadways to have a maximum speed at these levels. And what the Insurance Institute for Highway Safety study found was that looking at just 2013 alone, the increases in these speed limits resulted in 1,900 additional deaths, which essentially cancels out the number of lives saved by the frontal airbags that year. So there's a trade-off in these increased speeds for the safety impact that we see there. So it's important for us to think about how speed limits and speeds are going to affect things and the safety impact that's going to result from those increases in speeds. A recent example of speed limit changes is a bill from North Dakota that would raise the speed limits to 80 miles per hour. I think most importantly, or interestingly, in the fiscal notes, they noted that the direct or initial fiscal impact would be $155,000, and that would be simply to change the speed limit signs on the affected roadways that had the speed limits raised to 80 miles an hour. But the follow-up and the longer-term fiscal impact is estimated at over $300 million to actually upgrade the facilities that had the increased speed limits to account for the increased lengths needed for acceleration and deceleration and sight distance and curvature. So it was interesting to see this in this bill, the kind of direct change in costs that would need to occur, and then the longer-term impact on changing those speed limits. Next, we're going to look at speeds on local roads, neighborhood streets. So as we think about some of these topics, we should keep in context the type of road that we're going to be looking at. And we're going to be focused on these neighborhood streets. And often, again, the complaint is not that speeds are too low, it's that speeds are too high. So a lot of local road complaints related to speed are that people are speeding through neighborhood streets that they think are excessive for the environment and for the context. So if you are on any type of neighborhood forums, you've likely seen this is one of those recurring themes. Speeding is in the neighborhood, and often though it's people who live in the neighborhood are the ones who are speeding through neighborhoods. There are several places that will have cut-through streets, and those may be non-local or non-neighborhood drivers, but typically a lot of the people that actually are speeding in neighborhoods are the people who live in those neighborhoods. This also, when we think about local streets, it has a name, and it's called traffic calming, when we think about trying to reduce or minimize those undesirable impacts while still maintaining accessibility and mobility through those neighborhood and local streets. So just as an example, this is a street in Raleigh, North Carolina. One horizontal curve at the beginning, and then it's essentially a quarter-mile tangent that doesn't do a lot to discourage high speeds. There's actually some vertical alignment on this as well. So a pretty long section of a downgrade, and then it's flat at the bottom. The posted speed limit is 25 miles per hour, and a speed study actually found that the maximum speed during this study period was 55 miles per hour. That was the only speed in the 50 to 60 mile per hour range, but still a substantial amount of traffic, almost 20%, was more than 5 miles an hour above the posted speed limit. And because of the nature of this street, it's a dead-end street, these are all people who live on the street. This is no cut-through traffic. So even people who are aware of concerns, complaints about speeds are the ones who are doing the speeding on this roadway. So just a local example, putting in context some of the potential speeding problems and the magnitude of that problem. There are lots of different treatments that can be used for trying to calm traffic, trying to reduce speeds or potentially even volumes. They can be horizontal elements, including mini or regular size roundabouts, chicanes, chokers, medians, semi-diverters, forced turns, cul-de-sacs. You can also have vertical elements like bumps, humps, raised intersections like a speed table, pavement irregularity. And we've got to think about also the spacing of these elements or these slow points to maintain midpoint speeds of 25 miles per hour. So if you're looking at trying to keep people at 25 miles per hour in between those slow points, the spacing of those slow points can be no more than 300 to 400 feet apart. So we can't just put one of these elements in on a long roadway and expect for speeds to stay low. A lot of studies have found that if you only put one, or you have a long distance between them, that people will try to make up for that lost time by speeding in between those slow points. So we've got to think about that human element, human behavior, the psychology behind drivers if we want to encourage lower speeds consistently. Speed limit reductions in and of themselves don't tend to be very effective, but they are fairly popular, as well as stop signs as a traffic calming device don't tend to work that well, but are again very popular. So there are lots of options out there. Some work better than others. A lot of cities have programs or plans or a toolbox that they'll use to implement some of these, experiment with others, and hopefully come up with something that works for their community and is effective and efficient. Here is an example in the town of Cary. Communities can request a mobile speed unit to communicate to drivers what their speed is, remind them of their speed relative to the speed limit. Here's an example from Raleigh of a full traffic calming process and a application form that people can communicate potential issues, describe the problem, and they share a lot of information about what are some of the things they're looking for, what are the specific factors. So they're looking for speeds of the cars that are traveling and how many of those are speeding. They want to look at the crash history. They want to look at pedestrian generators in this larger process that's going to seek feedback from the residents. It's going to allow for public comment. There's going to be a final design meeting and then a ballot of whether or not the final traffic calming option is going to be implemented. So it is a fairly lengthy process that involves more than just one household that may be complaining. It's going to take a neighborhood vote in order to implement something. And many cities and towns have processes that look like this. Here's an example from the city of Charlotte, some of the treatments that they use and the process for implementing those. They require 60% of property owners to sign saying that they want something installed in their area to try to reduce speeds or to calm the traffic. Here's some other treatments, some newer treatments, some less common treatments. One is the speed kidney, and so it's kind of adding in some horizontal and vertical elements all at once. So drivers have the option to either use the vertical elements by driving over these parts of the speed kidney, or turn it into a horizontal element by driving a curved path through the speed kidney. The speed cushion is another similar type concept that are used to allow cutouts for larger vehicles, in particular buses and emergency vehicles that wouldn't actually have to drive up on the speed cushion to be able to go through them. That's one of the common complaints about any vertical traffic calming measure, is that it slows down or has the potential to slow down emergency vehicles. And so the speed cushion, similar to the speed kidney, are trying to adapt and respond to that complaint. The city of Monroe, North Carolina, uses speed cushions in several locations, and this is what it looks like in practice. Lots of cities are also trying temporary things before they put in something permanent. It's the idea of spending $1,000 before you spend $1 million. So if you see the images on the right, this is a very temporary setup to see is this going to work before going back and actually adding more permanent elements. I think that's a great way to test out traffic calming measures to make sure that they are going to have the intended effect, that people will understand them, and it gives you an easy way to modify things before you actually start putting concrete down. Here's another example of testing something. This is also known as tactical urbanism. This is a neighborhood street that wanted to try to reduce the speeds. We can see it's a very flat, very straight roadway, a 38-foot curb to curve width. And so the thought is, what if we kind of add in our own kind of choker element here to reduce the width of the roadway to 24 feet, which is still two 12-foot lanes, so still plenty of room for mobility there, but just squeezing in the traffic a little bit, creating a little bit of friction to try to reduce the speeds on this roadway. And so this concept can be implemented very simply, very quickly, just to test and see what the effect is. Maybe even testing how frequently you need these slow points before putting in something more permanent with concrete or other materials. This is an example from the city of Charlotte of just kind of opening up all the different options, or a larger toolbox of things that can be done to try to calm traffic. And some of these don't necessarily fit into traffic calming, but it's falling under this umbrella of calling it placemaking. And so some of the things, sidewalk dining, painting the pavement, parklets, all could have this effect of changing that environment, changing that roadway environment to calm the traffic in those areas. When we're looking at the implementation and evaluation of traffic calming, it is a well-accepted retrofit. A lot of communities, if you follow neighborhood forums, a lot of them are asking for things that may not be appropriate for the location, but they may be asking for speed bumps or speed humps or more stop signs or lower speed limits. So there's already an awareness that traffic calming can happen and can be effective. There are many alternatives. Traffic control devices can be used. They're generally not as successful as some of the more physical elements to have the desired impact. Cities and towns need to have a plan and an involvement process and clear objectives, and that has changed tremendously over the past 10 or 20 years, that plans have a much more formal process to listen to those complaints, to address those complaints, and find a solution that's going to work for those communities. We do need to consider the system-wide impacts. Often what can happen, especially if you have a grid system, you may fix the problem on one street, but you may just migrate that problem to the next street over. So we do have to think about the system-wide impacts. The city of Portland actually does this. So this graph shows acceptable increases in traffic volume on the non-project streets. So looking at the traffic volumes on adjacent streets and seeing how much of an increase you're going to allow before you then need to do something on that non-project street. So at low vehicles per day, you may accept an additional 100 or 200 vehicles per day on that street, and that may go up as your vehicles per day increases, and that's what their lines show. So at 2,000 vehicles per day in the pre-test, if we go to the kind of the base condition here, that roadway would accept about 400 vehicles per day in the after period before they say, okay, something needs to be done to improve this now non-project street, but that's in the vicinity of some improvement that we made on an adjacent street, and now some of that traffic is migrating, some of that issue is now migrating to another adjacent street that may need to be addressed. So there's a lot of advantages for traffic calming, and again, all this is under the umbrella of speeds and speed limits. It can reduce vehicular speeds, it can reduce the number and severity of collisions, encouraging walking and cycling, reducing the dominance of vehicles. But it can also have some disadvantages. A lot of times people complain about discomfort, particularly for vertical elements. It can cause damage to vehicles and increase the maintenance cost to go out and maintain particularly vertical elements like speed bumps and speed humps. There are complaints about increasing emergency vehicle and bus travel times over these elements. Noise and emissions can be a result. They can be costly to install and then remove if they need to be removed later. And there's a lot of potential input and opposition from residents and from commuters. So a lot of things to think about when implementing a traffic calming program or project. Now we'll review setting speed limits. This information is based on an NCDOT sponsored research project looking at developing guidelines and documenting engineering studies for establishing speed limits. So within North Carolina, the law establishes statutory speed limits, 35 miles per hour inside municipal corporate limits and 55 miles per hour outside those limits. But ordinances can be used based on an engineering and traffic investigation by NCDOT to change those speed limits. Something that comes up a lot, and I want to go ahead and establish what it is the 85th percentile speed. This is a fairly misunderstood and often misused piece of information, but it is important to understand vehicle speeds. And so when we look at speed studies and assessing what current vehicle speeds are, 85th percentile speed is one that's used, and again, it is an important piece of information that can be used and can influence the ultimate speed limit that is selected. The 85th percentile speed is the point in the speed distribution at which 85% of the vehicles travel at or below. So if we look at this distribution, the 85th percentile speed is 33.2 miles per hour, and this is telling us that 85% of the drivers on this road drive at 33.2 miles per hour or slower. So only 15% are driving faster than 33.2 miles per hour for this example. So the use of the 85th percentile speed is based on the theory that the vast majority of drivers are reasonable and prudent, that they don't want to be involved in a crash, they desire to reach their destination in the shortest possible time. And a speed at or below the 85th percentile under good weather and visibility conditions may be considered as the maximum safe speed for that location. That's generally how traffic engineers have approached the 85th percentile speed. A lot of before and after studies have substantiated the general value of the 85th percentile criterion. It's also proved that and shown that the 85th percentile speed is one characteristic of traffic speed that most closely conforms to a speed limit that is considered safe and reasonable. So there is a lot of history and importance and usefulness of the 85th percentile speed, and something that needs to be considered as you're setting speed. But the Federal Highway Administration has clarified that that speed limits are not required to be set based on the 85th percentile or other operating speeds. And a review of practices and safety evidence for setting and enforcing speed limits on all types of road noted that the practice of setting speed limits at the 85th percentile or some other related operating speed measure relies on the assumption that most drivers are capable of judging the speed at which they can safely travel, which may not be the case, and that assumption should be questioned, and we should always dig into it and decide whether or not that the operating speeds and whether or not the operating speed should be the primary driver of that speed selection. And there's other characteristics that we'll talk about that we looked at in this research study that are important to consider. So when we look at a traffic study, the MUTCD tells us that speed zones shall only be established on the basis of an engineering study in accordance with traffic engineering practices. And within NCDOT policy, there's not very much prescriptive guidance here, and there's a lot of room for engineering judgment, but the policy does state that several topographic and traffic characteristics should be considered and should be considered together, enabling the investigator to arrive at a sound decision for the proper speed limit. So some of the things that should be considered when we look at engineering judgment that needs to be built into deciding an appropriate speed limit. And again, there is a lack of prescriptive standard or equation. There's no 16 variable equation that says you plug in all these, you plug in your numbers from these specific situation and we're going to tell you what the speed limit should be. There's just lots of factors to consider, including the area type, the number of driveways and intersection types, the presence and type of multimodal facilities, crash history, surface treatment, shoulders, a driving investigation. Lots of things can go into these. Lots of these have other subsets. You know, there are bike lanes, are there parking lanes, are there bus stops, are there sidewalks, are there raised pavement markers, are there how many lanes are there? So lots of things can be built into this overall engineering judgment that's needed to decide the appropriate speed limit. US Limits is a tool. It's an expert system that has been used and developed to check the appropriateness of the maximum speed limit recommendations. But even in US Limits, they do recommend engineering experience and knowledge should be used when interpreting the results from that expert system. There are challenges to the decisions about speed limits. And this is why speed limits are particularly difficult and of particular concern. The original engineer who decided on the speed limit may not be available anymore to defend or at least explain why the speed limit was selected. And that's why in a couple of slides I'll share an overall documentation type of process. But lawsuits do challenge speed limits regularly. Problems can arise if that original engineer is unavailable, and there can be, because of the engineering judgment that's required, a lot of variability in speed limit assessment and recording of the speed limit decision. So this process to document the judgment includes determining what information you need to collect. So even kind of right at the beginning, part of the judgment says, well, we need to decide what information we want to collect. Then actually collecting that information, analyzing the information, and then deciding what speed limit is appropriate. So some of the information in the research project provides more information. I'm just going to provide a snippet of each of these steps, but the full research study is available if you'd like to dig into that in more detail. So some of the things that you may need to consider, and even extremely important, is how does the road segmented? So is it between major intersections that you're looking at trying to have a consistent speed limit? Is it a certain distance? We're going to chop the road into 10-mile segments. How is that done? And so some of the recommendations we have for this based on previous research is if the driveway density changes, if there's a change in the crash pattern, does the roadway cross-section change once it's outside the intersection influence area? Does the land use change? Lots of things can go into the actual segmentation, because that's the basis of the data that are going to be collected, is what are the portions of roadway as you move along a segment or an entire corridor. How many different pieces or stretches of road do you need to look at independently to try to establish what the safe speed limit should be? Next, we need to collect the information. So after we've decided what we're going to collect and how we're going to segment the road, we need to go and collect a lot of basic information. So we need to know where each of these locations are, what the county is, what the current speed limit is, upstream and downstream speed limits. You need to follow a standard data collection procedure for all of these and save them in a common file in a common location so they can be found and updated in the future if needed. Here's some other examples of some of the information that would go into this if you decide it's necessary. So the types of multimodal facilities, the crash information along the corridor. A lot of this can be collected in the office before you even do a site visit, which can then help inform some of the other pieces of information and or observations you may need to make when you're actually in the field. So some of the field information, you may need to look at the surface treatment and its condition, similar for the shoulders, any other things that may help influence a speed limit decision. And then analyzing the information, what we've put together is a list of the elements that can influence the speed limit, and we just help the engineer at this point document whether or not those elements either weren't evaluated or are not applicable, but then more importantly, whether it supports reducing the speed limit, no change in the speed limit, or increasing the speed limit. And then also give an option to check whether that element is critical. So we took a lot of information in and then built this set of elements, and there is an other category here as well. But the idea is to look through each of these types of data individually and document what decision it supports, identifying the data types that are critical considerations and that will ultimately influence the speed limit that is selected. Our research did allow us to share some guidance on factors to consider. So for example, driveways and intersections, an increase in the access density, so the increase in the number of driveways and intersections, generally supports lower speeds. One of the notes we have there is that 40 or more per mile is typically the range for starting to have significant impacts. You may look at alignment and curves. So generally an increase in the grade of the roadway or the sharpness of curves generally supports lower speeds. And a ball bank study can be used for advisory speeds in the case of very sharp horizontal curves. So these are, again, just some of the elements that research shows us has an influence on speed limits. And then finally, we have actually rendering a decision and the opportunity to provide a narrative that highlights the critical elements or any other additional factors that contributed to the decision, and then ultimately a final recommended speed limit.